Welcome to Vectors. We'll discuss operating on vectors. This will get a person completely unfamiliar with vectors an ability to understand what's going on. It's normal to think of a vector as represented by an arrow, since a vector has both magnitude and direction. A vector U can be added to a vector V by adding corresponding components of the vector, where a component is the magnitude of the vector along an axis, that is, what it's projected onto the axis to be. There are two ways of representing a vector in common usage. We'll take an example of a vector with a magnitude of 2 units in the x direction, 3 units in the y direction, and 4 units in the z direction. And it can be represented in bracket notation, which is this, or with unit vector notation, which is, these are the unit vectors, or vectors magnitude 1 in the x, y, and z directions. So this vector 2, 3, 4 is equal to 2i plus 3j plus 4k. I like the bracket notation a lot better. So we'll have an example here. We're going to add two vectors together. We add corresponding components. 3 plus 2, negative 4 plus 6, 1 plus negative 9. And we find out we have a vector with 5 units in the x direction, 2 in the y, negative 8 in z. Subtraction works pretty much the same way. We're going to subtract the various components. So we'll subtract one vector from another, and we will end up with 3 minus 2, negative 4 minus 6, 1 minus negative 9, or 1 negative 10, 10. To visualize addition of vectors with arrows, place the tail of one arrow, or the arrow representing one of the vectors, at the head of the other. There will be a visual representation of this, with a yellow arrow being added to a purple arrow, and the sum will be the red arrow. So this will represent vector addition. Here we have the yellow arrow, a vector, purple arrow, a vector, and we're going to add them. Notice that the vector, the sum vector, has a smaller magnitude than the sum of the two magnitudes of the vectors being added together. That's normal unless they're in the same direction. Often we need the components of a vector. A component of a vector is the projection of the vector onto an axis. So here we have a vector, the red vector V, has an x component, the black vector, plus a y component, the y vector. Using a little trig, we find that the x component is v cosine theta, and the y component is v sine theta, where theta is the angle between the vector and the x-axis. The magnitude of a vector is called its norm. It's given by the Pythagorean theorem using the magnitudes of the components. For a two-dimensional vector, the norm is, and the symbol that looks like a double absolute value bar, and for good reason. The horizontal component squared plus the vertical component squared. So it's just a Pythagorean theorem of the components squared. For a three-dimensional vector, the norm is, and we use the three-dimensional Pythagorean theorem, which looks a lot like the two-dimensional Pythagorean theorem, except it has another component. Now, multiplication, we have to be careful. There are three types of multiplication involving vectors. First, we'll discuss multiplication by a scalar, the simple one. Multiply each component of the vector by the scalar. This gives a new vector in the same or opposite negatives. If we have a negative scalar, it's the opposite direction of the original vector. So multiplication by a scalar does not change the direction of the vector, only the magnitude. Example, find the momentum, and this is the symbol for momentum, equals mass times velocity, where the mass is 2 kilograms and the velocity, being a vector, is given by 341 meters per second. Momentum is 2 times the vector for v, 341 kilogram meters per second, or 6 times 3, 8 times 4, 2 times 1 kilogram meters per second. The dot product produces a scalar. It is found by multiplying corresponding components of two vectors and adding the products. So if I put a dot, and we know there are different symbols in multiplication, in vectors, that makes a big difference. So we're going to find a dot product of 2, 4, negative 2, 3, negative 4, 2. We'll multiply 2 times 3. We'll multiply 4 times negative 4. We'll multiply negative 2 times 2, and we'll find out we have negative 14, a scalar. The angle between vectors u and v is given by the equation cosine theta is u dot v over the norm of u times the norm of v. So we solve that for theta, and that expression gives us, you have to be taking it or cosine of each side. Theta equals the or cosine of u dot v over the norm of u times the norm of v. If the dot product is 0, the two vectors are orthogonal or perpendicular. After all, the cosine of 90 degrees is 0. Finally, the cross product of two vectors, u cross v. This one, we need determinants. So it's u cross v is the determinant. And here we don't have much choice about the notation. We use I, j, and k, the unit vectors. The components of u make up the second row, and the components of v make up the third row. This is going to be I times these four, a 2x2 determinant, uy, use the vy vz, minus j times ux uz vx vz. There's a little typo here. That should be an x. Plus k and we take these four, ux, uy, bx, by. And the way we find a determinant is we take the diagonal and multiply. So this would be uy, bz minus, and we take the reverse diagonal. So this would be uz, by. And we do the same for each of these to evaluate the determinants. This technique of taking a 3x3 determinant and reducing it to 2x2 determinants is called expansion by minus. This is a 3x3, a little difficult to handle. Sometimes a textbook will just give this and ask you to memorize as the answer. I like to go through the step. It's more important that we understand where it's coming from. One little quirk is if I reverse the order of u and v, have v cross u, I get a negative sign. Now, the physical meaning of the cross product is that we're getting a vector and it's perpendicular to the plane of the two vectors we're multiplying. So we have two vectors in one plane, let's say the xy plane. The cross product would be in the z plane, and sometimes they'll be oriented upward and sometimes it will be oriented downward, and that comes out of the calculation. So not always will the vectors be in the xy plane. They might be tilted. The cross product will be perpendicular to the plane that will contain those two vectors. And the cross product is a vector.